everything you look at on the left-hand side, this, even though that internal moment depends on the curvature, but when there's no force, no lateral force on the right-hand side of your governing equation, that means the curvature is also completely dependent on your axial force, which means the curvature, as you know, curvature is related to moment. So that means internal moment is dependent on the axial force in the case of beam buckling. I'm sorry, column buckling, which is this one right here on the left. But when you have lateral loadings, your moment will be affected by the lateral force as well. So the two things we know is different. The first one is deflection will be different, and the second one is the moment will be changed too. So here we can just write down the summary here. First, deflection, not just the maximum, right? Deflection will be amplified in beam columns compared to the buckling of columns. Next one is internal moment. Will also be amplified because of the non-zero terms on the right-hand side of the equation. So that result is here. That result is...
Professor, can you just go back for one quick second?
Yeah.
Awesome, thank you.
The amplified the maximum moment also equals to this, and the that is WOL squared over 8 times an amplification factor, which is 2 times the second U minus 1 over U squared. Now, for the purpose of design, we're going to call this first coefficient, we're going to call it M naught. So that means that's also the linear term. And the second part in this expression will be for the buckling effect, which is the nonlinear part. And in here, we can also express this maximum moment in this way. We can call this to be M naught times 1 plus 1.028 times the ratio between P and PE, and times a series of these terms, which is the P over PE dependent. The first one is the linear term, which is 1 plus P over PE and plus P over PE squared, and so on and so forth. So this is the approximate, which is a Taylor expansion for the maximum moment. And this can be further approximated by this expression, which is M naught times just this, which is 1 minus P over PE. Upstairs is 1 plus 1.028 times P over PE. And then finally, we say that this can be further. Well, actually, this coefficient here is not quite right, and this one should be 0. And then finally, we say that this whole thing can also be approximated by just this. And of course, the last one is highly simplified. So this is a simplified expression. Nonetheless, from this expression, it does indicate the amplification of moment due to the application of axial force. So when you see the expression of a maximum as a function of axial force, you know that the bending moment will be amplified by axial force. Right? Now, if you look at this, tell me, what happens if you look at just the mass, just the mathematics here? When P is 0, everything within the square bracket becomes what? Becomes 1. So that, what does that mean?
It's equal to 0.
No, they cannot be 0. When P becomes 0, the entire square bracket becomes unity. That means there's no amplification, right? Everything goes back to what? In this case, is WL squared over 8. That is a linear effect, which makes sense, right? When there's no axial force, there's no moment amplification. Of course, that makes sense. Now, when P becomes very, very large, right? What happens when P becomes PE here?
Maximum moment goes to infinity.
Yes, that means it's buckling, right? At the moment of buckling, the moment the deflection goes to approaches to infinity, so does the maximum moment. But when P is very large, but is not at the PE, in here this ratio will become very large. That means that shows the nonlinear amplification of internal moment, and the same effect applies to maximum deflection as well, right here. Okay, which is the figure I show it on my slide, and this is on my slide, page number 8, and also page number 10. You can just write it, and you don't have to copy it.
Professor, is that number over there is like 0.028?
Yes,
It's what? The top one.
the top one is 1. Top one is 1.028.
Okay, the second one is 0.
Yes.
Okay, thank you.
Can you please lower your professor?
Yeah.
Got it. Thank you.
Yep. All right. And so I think we can move to the next example. The next example we're going to consider is the case of end moments. So this will be page 51. Okay. What is this problem? This problem is about an end moment. This, and we have an axial force acting right here, and of course it produces reaction force right here, and you also have a external moment acting at support B. So on the left, that's A, on the right, that's B. So that means you have a clockwise end moment. And B acting here, and another clockwise end moment acting at A. And everything else is the same, which means you still have the total length being L, and EI is constant. This is L and EI is constant. So what do we need to do? Find the PCR. The same thing, right? Okay. And for the moments, actually, it's relatively easier in terms of analysis, because what we have trying to do is to find out the moment if the problem already tells you what is the end moment that you have to consider, and your moment diagram becomes super easy. In this case, there's no lateral force acting on the beam column, which makes the analysis very, very simple. If you have a lateral force in it, what do we do? Suppose, can we consider the case combining these, combining the end moments, and what if there's another force, right? Acting maybe somewhere here. Let's call Q. Can we consider that? Yes, and you already know that that application Q here will not change your critical load, but you will only change your maximum moment. You will change your deflection, right? So then, how do you solve these kind of problems? Suppose I have this, and what if I also want to consider uniform disability loading, just to make things a little bit challenging and interesting, right? So what do we do? If you have combined loading, you can separate them one by one, and then you use the principle of superposition to put them together. However, be careful. In the final solution, like this, in the last case, when we consider the combined effect of axial force and the lateral loading, in this case, the uniform disability loading, right? In this case, we purposely separate the linear effect as y naught here and everything nonlinear in the second part. When you have combined loadings, and if you want to use the result from the notes or from the textbooks, you always will keep the linear term the same. That means when you have combined loadings acting on the beam columns, this term here will change. The square bracket will carry different form, but your linear term will always be the same. So just keep that in mind. And for that, you can actually use principle of superposition to find out what is the revised expression for the buckling effect, which is the squared bracket here. So for that, you can use principle of superposition to find it. Now, so we can start with few steps. Probably we will not be able to finish this problem, but we probably should be able to find the expression of deflection. That's very easy. So first of all, before we have the free body diagram, let's find out all the reactions here. Here we have summation of forces, horizontal force to be 0, and of course we did not consider the actual force here. Do we have vertical reactions in this problem? Do we have?
Yes.
Yes, we do, right? And what will be the direction?
Down.
At B, starting with B, is up or down?
Up.
It's up, right? At B, it should be up. And what about at A?
Down.
Down.
A should be down. Why should be down? Well, force equilibrium, right? If you have one to be up, the other must be down. Now, look at the quantities. What will be the quantities for the reaction at B? So let's call it RB.